You can see that the general description of video number 18 is kind of long and complicated looking. I will say at the start here that the question itself is not quite as hard as this makes it seem. However, this description is accurate, and it's something you should get used to as you work through probability and statistics, so I wanted to go ahead and write it this way. We'll be finding a probability involving the sum of two independent and identically distributed discrete random variables. That's quite a mouthful. But we're using things we're familiar with, using the special addition rule for mutually exclusive events and the special multiplication rule for independent events. In doing this, I also want to introduce the idea of a discrete convolution, kind of an advanced concept that comes up when you're adding random variables. Both random variables and convolutions have continuous counterparts. We'll be getting to those things in much later videos. Here we have it. The question is number 16. It says an insurance company determines that capital N, remember, capital letters refer to random variables. It's the number of claims received in a week, a random week. Think about that. That would have to be discrete because it can only take on whole number values starting at 0. Could be 0, could be 1, could be 2, could be 3, could be 4, etc. There's no clear upper limit on how big it could be. It's a random variable that is discrete, and therefore, as we saw in video number 17, it has a probability mass function, or PMF. This thing right here is the probability mass function that is defined for n greater than or equal to 0, and it's again understood that n must be 0, 1, 2, 3, 4, etc. N can't be pi, you can't have pi claims. N can't be 4.7, you can't have 4.7 claims. It says the probability that the random variable capital N during a given week takes on a value little n, think of little n as something specific, is given by this formula. So for example, if you're wondering what are the chances that next week there will be 3 claims, little n is 3, replace little n with 3 here and get 1 over 2 to the 4th, 1/16. Okay, that's our PMF. I will, in this video and any video where I talk about PMFs of discrete random variables, also write it as little p of little n. That's function notation. P is the name of this function, little p here. Capital P just emphasizes probability. Probability of this event occurring equals this formula. This as a function of little n, though, could be written as P of n. You will see people write it as F of n as well. Okay, I'm going to use F more in the continuous case. Okay, I think it's better to use P here in the discrete case. All right, the company also determines that the number of claims received in any given week is independent. Oh, that's always an important word in probability and statistics. Independent of the number of claims received in any other week. Okay. Calculate the probability that exactly 7 claims will be received, not during 1 week, but a 2-week period. Whoa, what in the world? If this is about 1-week periods, how are we going to possibly deal with 2-week periods? Well, don't panic. Take a deep breath and just think of it step by step. We want to find the probability that the number of claims in a 2-week period equals 7 exactly. It's maybe not clear how to write that. Should I say the probability that n plus n equals 7? Well, you could, but it's not ideal. It's better instead to say let n1 be the number of claims in the first week and n2 be the number of claims in the second week, and say you want to find the chances that this sum, n1 plus n2, equals 7. But if I'm calling them n1 and n2, is that okay? Are they both the same as n? The answer is yes, because they are identically distributed. This is the PMF for a week, and it's any week. It can be the first week and the second week. Both n1 and n2 are the same random variable, essentially. They both had this distribution. They had the same PMF, the same probability mass function. Can be used for both of them. Okay, that's the first conceptual hurdle to get over. What next? So then you scratch your head and say, how can this happen? How can n1 plus n2 be 7? Well, n1 could be 0 and n2 could be 7. n1 could be 1 and n2 could be 6. n1 could be 2 and n2 could be 5, etc. n1 could be 7 and n2 could be 0. Those are a bunch of different events where the sum is 7, and they are mutually exclusive. They can't occur at the same time. I need the special addition rule for mutually exclusive events. Now, I'm not going to write all this out because it would take too much time, but let's just see the pattern here. One event where the sum is 7 is when n1 is 0 and n2 is 7. That's one way the sum can be 7. Or, so I'm using ands and ors here instead of intersections and unions, which seems more appropriate because I'm not thinking of these events as sets, I'm more describing them in terms of these equalities here. Or n1 is 1 and n2 is 7, or 6, excuse me. Or, etc. The last one would be n1 is 7 and n2 is 0. Can you see that okay? All right. So a bunch of events connected by ors, and these are all mutually exclusive events by the special addition rule for mutually exclusive events. This is the sum of a bunch of probabilities. I guess would be 8 probabilities here. The probability that n1 is 0 and n2 is 7, plus the probability that n1 is 1 and n2 is 6, plus the probability that n1 is 2 and n2 is 5, plus the probability that n1 is 3 and n2 is 4, etc. Then what do? Can you make a guess? You see a bunch of ands here in each of these. Those are like intersections. I need the special multiplication rule for independent events. I'm assuming independence. Each of these is a product of unconditional probabilities. This is the special multiplication rule, not the general multiplication rule. I need that assumption of independence to help me finish this problem. And for each one of these probabilities that you see here, I can use the given PMF, this formula up here, P of n here. Yeah, I could write it in terms of little p of n here. And again, it doesn't matter that these have different subscripts because they have the same distribution. This is little p of 0, this is little p of 7. Then I get little p of 1 times little p of 6 right there, plus little p of 2 times little p of 5, etc. The last one is going to be little p of 7 times little p of 0. If you think about it, by the symmetry of this, I could really just go through little p of 3 times little p of 4 and then double the answer as well. Let me just leave it like this, though. Little p of 0, plug in little n equals 0 here, get 1/2. Little p of 7, plug in little n equals 7, get 1 over 2 to the 8th. Then I get p of 1 is going to be 1 over 2 squared, and p of 6 is going to be 1 over 2 to the 7th. Then I get 1 over 2 cubed times 1 over 2 to the 6th, etc. Each one of these, in fact, has got to be 1 over 2 to the 9th. And there's eight of these terms, right? Think about that, because focus on like this n1 starting at 0 and going up to 7. There's 8 terms in this sum. So this is really 8 over 2 to the 9th, 2 to the 3rd over 2 to the 9th. You can do this without a calculator. 1 over 2 to the 6th, which is 1/64. That is the correct answer, although I forgot to look at the online sample exam ahead of time to see which choice it was. But this is the correct answer, 1 over 64. Okay? All right, let's take a step back and think about this more generally and talk about discrete convolutions as well. Actually, before I talk about discrete convolutions and generalize what I did here, I would like to emphasize that the sum of these things must equal 1. This is going to be a PMF. All the probabilities have to be greater than or equal to 0, which they definitely are. Do they all sum to 1 as n goes from 0 to infinity? That should be checked. And you might also wonder, what What if the 2 were a 3 or a 4 or a 5? Would that work as well? Well, not as a PMF, because the sum wouldn't equal 1. But maybe we could have a numerator that adjusts for that. Now let's actually think about that first. Let's think about an infinite sum of some constant, I'll call it b, over, say, a to the n plus 1 as n goes from 0 to infinity. Okay? What relationship would be necessary between a and b for this to converge to 1? And also, is there a condition on a itself to make sure this converges in the first place? If you think about that, I hope you realize a would have to be bigger than 1. If you write this infinite sum, this infinite series out the long way, it's going to be b over a when n equals 0, plus b over a squared when n equals 1, b over a cubed when n equals 2, etc. forever. It's an infinite sum. Little secret about infinite sums, you're not literally adding infinitely many things. It's really a limiting process. Does this converge? This converges if what? If the common ratio, the thing I need to multiply each term by to get the next term, is less than 1 in absolute value. The common ratio here, if you think about it, is 1 over a. Is that less than 1 in absolute value? This is true if a is bigger than 1, which I mentioned a minute ago. It would also be true if a is less than negative 1, but that could run us into trouble with getting negative probabilities. We would want to avoid that. We're going to consider the case where a is bigger than 1. So 1 over a is the common ratio. What's the first term? It's b over a. This is going to converge to the first term divided by 1 minus the common ratio. This is a very important formula. It's called the formula for the sum of an infinite geometric series. You will need this in probability. You'll need it in financial math, especially financial math. If you want to be an actuary, it comes up all the time. First term is b over a. Common ratio is 1 over a. If you multiply the top and the bottom of this by a, you get b over a minus 1. And so if this is going to equal 1, b will have to equal a minus 1. If I set this equal to 1, that'll be true if and only if b equals a minus 1. Okay? So if you had a 3 to the n plus 1 in the denominator there, you'd have to have a 3 minus 1 or 2 up on top to make it a valid PMF. Okay, so that was a side issue I wanted to talk about, but I think it was worth it because it will come up later. Let's talk about convolution now. Discrete convolution. And by the way, I'm going to show you some things in Mathematica, including a graph here at the end. Think about the general case here. What is the PMF of n1 plus n2? In other words, how in general would you find this probability where little n is 0, 1, 2, 3, etc.? By analogy with what we did here, you could use the special addition rule for mutually exclusive events and the special multiplication rule for independent events to write it as a sum, kind of like this. Well, actually, I'll focus on this form of it. Initially, a sum, k goes from 0 to n. In our case, little n was 7. Think about the pattern there, it would work to go p of k times p of n minus k. Like here k is 0, n minus k is 7 minus 0 is 7. Here k is 1, 7 minus 1 is 6, then k would be 2, 7 minus 2 would be 5. That's how you write it. This is a discrete convolution. Discrete convolution. Just a little notation. People would sometimes write it as p star p of n, where the star is your discrete convolution operator. Convolving, people sometimes say. At the moment, it's just an operation. It's just a way to combine p with itself to form a new function of n. I did combine p with itself here because these two variables have the same distribution. It is in general, a useful thing to form a discrete convolution when you have two discrete random variables that might have different distributions, and you'd convolve those two PMFs for those two random variables. Okay? There's a continuous analog to this involving integrals instead of sums, but that's just a little terminology, a discrete convolution. In this case, it does simplify. Let's go back to our situation here where P of k would be 1 over 2 to the k plus 1. And so P of n minus k would be 1 over 2 to the n minus k plus 1. Oops, that's a minus sign there. N minus k plus 1. Simplify this. You're going to get 1 over, let's see, the k's will cancel. You'll get 1 over 2 to the n plus 2. That's a constant in k, so you've got n plus 1 of those. This is going to equal n plus 1 over 2 to the n plus 2. That would be the PMF for the sum of these two random variables, these two independent and identically distributed random variables. So its sum must equal 1 as well. This must be true, though that's a little harder to check because it's no longer a geometric series. Let's have Mathematica check it for us. Let's see, where's my Mathematica? Here we go. So first I'm going to do some computations, and then I'm going to show you a graph. So this is the infinite sum that was a geometric series. Actually, I'm using a 1 here instead of a b. But this does emphasize if for an arbitrary a, if you want this to equal 1, I better use b equals a minus 1, so I get a minus 1 over a minus 1. And that's what I do here. So this is the general PMF for a problem involving an arbitrary a, and it does converge to 1. If a happens to be true, like in our problem, you get this. These are our two different ways of getting the answer of 1/64. This is the convolution, essentially. I'm calling it p-sum because it involves the sum of two random variables, n1 and n2. Convolving p with itself, here's its general formula. If a equals 2, it equals this, which is what I wrote down a minute ago. Does, for example, when a equal 2, this sum to 1, Mathematica confirms that it does sum to 1. Let's end with looking at a manipulate of a couple plots. One plot is the discrete plot of the PMF of the general such situation where for an arbitrary a, and one is for the sum of the two random variables n1 plus n2. And technically speaking, these graphs go on forever. I'm only showing them up to n equals 10. The red graph is the original PDF set, start with a equal to 2 here. So the probability of getting n equal to 0, n1 is 0 or n2 is 0 is 1/2. The probability that n equals 1 is 1/4 here. You can't see it quite behind this blue dot, but it is back there. Probability that n equals 2, that was 1/8. Yep, 1/8 there. Then 1/16, then 1/32, etc. The blue graph is the PMF for the sum of the two random variables, n1 plus n2, and it starts out lower but gets higher. You add up all these heights, they have to equal 1. Let's see what happens as a changes. It's kind of interesting. As a goes up, here's how it changes. And you can see that except for when n equals 0, the blue graph actually seems to be above the red graph, except when n equals 0. On the other hand, when a is smaller, then the blue graph mostly goes below the red graph, except over here. Then it's above. Think about that intuitively. Think about that if that makes sense or not. Okay, thanks for watching.